Welcome to this explainer. Today we're taking everyday fluid behaviors and translating them into the hardcore math you need to crush exams like the JE. If you've ever stared at a dense fluid dynamics equation and felt totally lost, don't worry, you are in the exact right place. We're going to break down the invisible rules governing water and air, and we're going to do it by looking at things you actually interact with every single day. Okay, here's our game plan. 1. The speed of leaks. 2. Fluids on the move. 3. The merry-go-round effect. 4. The Venturi meter. And finally, 5. The soap bubble secret. Let's jump right in. Section 1. The speed of leaks. Picture this. You've got a leaking tank of water, maybe a punctured water bottle or a big garden rain barrel. We want to know exactly how fast that water shoots out and exactly where it's going to land. It sounds like a tricky physics problem, right? But fluid mechanics actually gives us an amazing shortcut. We can figure this out using Bernoulli's equation to derive what's known as Torricelli's law. When you apply Bernoulli's to both the top surface of the water and that tiny hole, which we call the orifice, something super convenient happens. Both of those spots are open to the atmosphere, meaning the pressure is exactly the same on both. So those terms just cancel out entirely. Plus, since the tank is massive compared to the tiny hole, the top water level drops so slowly that we can just treat its downward velocity as 0. What we're left with is this beautifully simple relationship between gravity, height, and speed. Solve it and your efflux velocity, v, equals the square root of 2gh. That literally means the water shoots out at the exact same speed as if a drop of water simply fell in free fall from that same height. How cool is that? And because we have that speed, we can use basic kinematics to find the horizontal range. Once the water leaves the hole, it traces a parabolic path, just like tossing a baseball horizontally. First, you find the time of flight based on how far it has to drop. Then, you multiply your horizontal velocity by that time, and boom, you get your range, r. It equals 2 times the square root of h times h minus h. Oh, and here's a massive pro tip to keep in your back pocket. That horizontal range hits its absolute maximum when the hole is punched exactly halfway down the tank. Moving right along to Section 2, Fluids on the Move. Let's take our fluids out of stationary tanks and put them in motion. Imagine you're holding a shallow bowl of soup in the passenger seat of a car. When the driver floors it, the liquid doesn't just stay flat relative to the bowl, does it? It sloshes and tilts backward towards you. Figuring out the why and how much behind that tilt is absolutely crucial for understanding fluid dynamics in moving frames. It all comes down to what we call the golden rule of fluids. Basically, a fluid surface is, well, it's lazy. It always wants to be level. But here's the catch. Level doesn't necessarily mean flat to the ground. It means the surface will always align itself perfectly perpendicular to the total combined push it's experiencing, the resultant effective acceleration. Let's break that push down. As the car speeds up with an acceleration of a0, the fluid feels this backward horizontal pseudo-force. At the exact same time, gravity, good old G, is pulling straight down. The tilt of the water, that angle theta, is just a tug of war between those two forces. So tan theta simply equals a0 divided by g. And if you take 2 points on that tilted surface separated by a distance L, finding their height difference is incredibly easy. h1 minus h2 just equals L times tan theta. It's really just elegant basic trigonometry hiding inside a physics problem. All right, Section 3, the merry-go-round effect. So, what if we take that exact same bowl of liquid, pull it out of the car, and put it on a spinning merry-go-round? Things get wild because the nature of the push fundamentally changes when you introduce rotation. We aren't dealing with a simple, flat slope anymore. With linear acceleration, you get a constant push backward. But rotational acceleration creates centrifugal force, which pushes the fluid outward toward the walls of the container. And here's the kicker. That outward push is not a constant. It actually gets stronger and stronger the further away you move from the center axis. Because that outward push is ramping up with the radius, the fluid literally climbs the walls, forming this beautiful curved bowl shape known as a paraboloid. Your effective acceleration here is variable. It's omega squared times r. Our lazy fluid is still just trying to stay perpendicular to the total force, right? But since the outward force keeps changing based on where it is, the surface has to constantly curve to compensate. If you integrate that changing slope, you get the total vertical rise at the edge. Height h equals omega squared times r squared, all over 2g. Let's transition to Section 4. The Venturi meter. We're jumping back to flowing fluids inside pipes. Now, the venturimeter looks completely intimidating on paper. It's a pipe that pinches down into a narrow throat and then flares back out, with little pressure tubes sticking out everywhere. But how on earth does that give us the fluid speed? Well, we can completely decode it by teaming up our continuity equation with Bernoulli's principle.
It's actually kind of magical when you step through it. First, the continuity equation tells us that when the pipe gets narrow, the fluid has absolutely no choice but to speed up. Then Bernoulli chimes in and says, hey, when velocity goes up, pressure has to go down. So the pressure in that narrow throat is literally lower than the pressure at the wide inlet. If you swap in your velocity relationships and factor out your initial velocity V1, you connect it straight to the pressure difference. And we can measure that pressure drop super easily by just looking at a height difference h in a YouTube manometer. By doing that, you perfectly isolate the inlet velocity. You're basically reading how fast the fluid is rushing through a hidden pipe just by looking at a liquid level in a tube.
And finally, Section 5, the soap bubble secret.
Let's zoom way in and talk about the microscopic side of things, surface tension. You'd probably assume that the math for a solid drop of water is exactly the same as blowing a hollow soap bubble floating in the air. I mean, they're both just liquid spheres, right? Actually, no. There is a massive plot twist here that catches so many students off guard.
The secret all comes down to the magic number 2.
Unlike a solid water droplet, which only has one single boundary, touching the outside air, a soap bubble is a hollow, thin film wrapping around a pocket of trapped air. That means it has an outer surface touching the outside air and an inner surface touching the inside air. Because of those two free surfaces, literally any calculation you do for surface area or surface energy has to be entirely doubled to account for both sides of the film. So let's say you're calculating the work done to blow one big soap bubble into n number of smaller bubbles. The entire formula scales up. A normal sphere's surface area is 4 pi r squared, but for soap bubble, the initial surface energy doubles to 8 pi r squared times the surface tension, T. When you calculate the total work done, which is just the final energy minus the initial energy, it comes out to 8 pi T times the quantity n r squared minus r squared. We literally just took the standard formula and swapped the 4 for an 8.
Now this right here is a golden cheat sheet. You'll definitely want to commit this to memory. It perfectly contrasts the work done for liquid drops, soap bubbles, and air bubbles trapped underwater. Look closely at the air bubble trapped in water. It only has one surface interface, the air inside touching the water outside, so it uses the 4 pi formula, exactly like a solid drop of water. Only the hollow soap bubble floating in the air gets the special doubled 8 pi formula. Getting this straight in your head will save you so much time on exam day.
Well, we've covered a ton of ground today, from predicting the range of water jets to unmasking the hidden geometry of spinning liquids and bubbles. Now that you've got a grip on the golden rule of fluids and the math making it all happen, I want to leave you with a thought. Knowing these invisible rules, from Torricelli's leaking tank to the double surfaces of a soap bubble, where else in the real world can you spot these equations playing out? Next time you're holding a coffee cup and an accelerating car, or just watching a bubble pop, look a little closer. Try to see the hidden geometry shaping the physical world right in front of you. Thanks for joining me on this explainer, and keep exploring.